My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. Good morning to all here in Bangladesh, and a very good evening to all those who are watching this program live from USA. So, hope you are well and safe from Corona pandemic. Today, I'd like to welcome you all to our 115th International Physics webinar. So, all we know that we are staying in a Corona pandemic situation, so we cannot continue our normal academic program inside the campus. So, we have to start our online programs. I think you have already come to know the Department of Physics, Pabna University of Science and Technology has already started its online program, including online international physics webinar. We have successfully completed our 114th international physics webinar, including two Nobel laureates. So today I would like to welcome you all to a joint session between the Department of Physics, Pabna University of Science and Technology, and the Department of Astronomy, San Diego State University, USA, in Astronomy. So we have with us here today Dr. Douglas C. Leonard, Associate Professor, Department of Astronomy, San Diego State University, USA, and he has already connected with us through online. So I'd like to welcome our speaker, sir. Good evening and good morning to here. So thanks for accepting our invitation, sir.
Absolutely. Thanks so much.
I would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, sir. So for those who are new, I'd like to inform that we have divided our webinar into three parts. First of all, we'd like to introduce our speaker with all of you, and then our speaker will deliver his speech, and at the end we have a discussion session. In that time anybody can join with us. So I think you have already come to know the title of this today's international physics webinar. Title is the on the explanation geometry of red supergiant stars, and our speaker is Dr. Douglas C. Leonard, Associate Professor, Department of Astronomy, San Diego State University, USA. And you can see his academic background. He has completed his BA in astronomy from University of Pennsylvania and MA in astronomy, University of California, and a PhD, University of California, and postdoc from Caltech. And we can see his career. He is working as the associate professor at San Diego State University since 2010 to now, and he served as an assistant professor at the same university from 2006 to 2010. So you can see his area of research interests: supernova, physics of supernova exploration, observational cosmology, and black holes. So you can see his publication. So he has already completed his more than 100 publication in different journal. So thanks for all of your patience. Now it's time to go to our speaker. So, sir, I would like to welcome you again, sir. Thanks again, sir. It's your time, sir. You can start your session, sir.
Thanks so much. I really appreciate it for the kind introduction and for arranging a talk that is my evening and your morning, so no one has to be up at midnight. So I'm beginning the talk by showing you probably my favorite picture of the night sky. It has my favorite part of the sky in it, and you may recognize the pattern of stars as the mighty hunter Orion. Most importantly to me, though, is that within this constellation sits probably the most famous star in the sky, which is Betelgeuse. Why do I like Betelgeuse so much? Well, there are two reasons. First, it's close. It's only 500 light years away, which means it's basically right in our backyard, astronomically speaking. But second, it's because it's an extremely rare kind of star. It's known as a red supergiant. Let me get my laser pointer going. A red supergiant, my favorite kind of star. And they're called red supergiants for obvious reason. First, they're red. That's what gets your attention when you see Betelgeuse in the sky. But second, it's an absolutely enormous star. It's huge. If you were to take Betelgeuse and sit it at the location of our sun, it would swallow up all of the terrestrial planets and then all the way out to the orbit of Jupiter. That's why we call it a supergiant. And what I love about red supergiant stars is that they always end their life in the same way. They blow up, they explode, as something called a supernova. These are rare stars. Only about 1 out of every 400 stars that nature gives us becomes a red supergiant. And you might ask, how do we know this is the fate that Betelgeuse is going to have? Well, I'm going to take you on a trip further away than Betelgeuse, much further away. What you're looking at now is a supernova that occurred in the year 2008 to us in a nearby galaxy, only 10 million light years away, called NGC 7793. And I want to be very clear about what you're looking at here. So in this image are actually three different things. First, this blobby kind of fuzzy smudge here, that's the galaxy. That's the unresolved light of probably 100 billion ordinary stars, all too distant and too faint to be seen individually. Second thing you're seeing are stars in the Milky Way. These are probably 10 or 100 light years away in our own galaxy, screening our view of this more distant galaxy. This is a single star 10 million light years away that just exploded. This is supernova 2008 BK. To be that bright in our sky and that far away means the luminosity of this object is about 1 billion times the luminosity of our sun. So let me tell you something that's amazing about this particular supernova. And here's that picture again. But here is an extreme close-up taken with very high resolution of a small patch of sky right around the supernova. But what makes this particular supernova so interesting is that a few years before the star exploded, somebody took a picture of this exact spot in the sky. And so we actually have a before picture before the star exploded. And this is in color because it was taken in multiple filters. And it's taken at a lower resolution than this picture, but you can match the stars up. This thing here is these two stars. This is that star. This star is that star. You can match them up. This one's fuzzier. But right at the location where supernova 2008 BK now sits a star that looks exactly like Betelgeuse. It's a red supergiant. We've played this game now for about a dozen distant supernovae, and in every case, it's a red supergiant sitting there. That's how we know Betelgeuse is going to end its life in this very same way. In case you're skeptical, and you should be, that this star actually exploded, in this case, we waited several years after the supernova and got another picture to prove, after all the embers and fireworks of the explosion disappeared, that the star was gone, which it has to be if it blew up. So definitive evidence, it's red supergiants that give rise to this kind of supernova. And it's exactly the kind of star that Betelgeuse is, that we think will explode. If you're curious about when Betelgeuse will explode, you may recall earlier this year, there was quite a lot of excitement about Betelgeuse. If you were watching the news, it was doing something kind of funny on its outer layers. It was kind of dimming a lot in its very outer layers. And so it led the press to get pretty excited about the idea that Betelgeuse might finally be ready to blow. And it actually reached kind of a fever pitch in like January. And then, of course, a few months went by and it didn't explode and the fervor died down, okay? And it still sits as just Betelgeuse in the shoulder of Orion today, not something rivaling the brightness of the full moon, which it will when it does explode. To try to give you a sense of when a star like Betelgeuse will explode, to talk about how stars end their lives, we first have to talk about how stars actually live. So let me just run through a little bit about stars' lives. If you think about a star, it's just a big ball of gas. And the life of a star is really a fundamental war being waged between gravity, trying to shrink the thing, and some force pushing out on the gas, keeping it nicely puffed up. That force is primarily the pressure exerted by newly minted photons coming from this extraordinary source of energy in the cores of all stars that are living, such as our sun, which is being pictured here. The fuel for most stars during the main part of their lives, like our sun, is the thermonuclear fusion of light elements into heavy elements. And for most stars during their lives, our sun right now, it's the fusion of the lightest element, hydrogen, into the next lightest element, helium, on the periodic table, which generates gamma ray photons and a bunch of other stuff, including neutrinos as well. The resultant photons pushing out against the outer layers as they scatter their way out of the opaque sun, that's what holds the sun and every star puffed up. The problem is, at some point, you run out of fuel. In this case, you run out of hydrogen in the core of the star where it's hot enough for it to fuse. And other elements, of course, can fuse. Helium can fuse into carbon and oxygen. And for stars like our sun, that will happen. The fusion of helium will begin in several billion years into carbon and oxygen. But after that, a funny thing happens. To fuse into elements heavier than carbon and oxygen, you need ever higher temperatures in the core. And for ordinary stars like our sun, the temperature just never gets hot enough to fuse carbon and oxygen, and the star dies. And the way the star dies is it's very gently. It shrinks down, compresses by about a factor of 1,000,000 in volume. And during the last thousands of years of its lives, it puffs out a lot of its mass into interstellar space, into a beautiful object known as a planetary nebula. This is what a dying low-mass star looks like, and our sun is a low-mass star, ultimately shrinking and shrinking until electron degeneracy pressure halts the contraction, and you get a white dwarf. A white dwarf is the fossil that results from 399 out of every 400 stars that nature gives us. And we see thousands of them littering the skies of our Milky Way. But notice there was no explosion in that whole story. The explosions come from these very rare stars that are born with more than 8 times the mass that our sun has. We call these high mass stars. Their fates are entirely different. And the reason their fates are entirely different is they can fuse beyond carbon and oxygen. But let me make 2 points right here. Let me just pause right here in the story. First, when they start fusing helium into carbon and oxygen, the temperatures in the cores of these high mass stars are so incredibly high that the battle between gravity pulling in and nuclear fire pushing out gets won by the nuclear forces, the forces of the photons pushing against the envelope. And it's during this phase that the star bloats up into this gargantuan giant that we call a red supergiant. So when you see a red supergiant, you know that hydrogen is done fusing in the core of that star. All right? At least it's helium fusing into carbon and oxygen. So we know that beetlejuice is nearing the end of its life, okay, by virtue of the fact that it's swelled up into this red supergiant. But unlike the case for low mass stars, once the high mass star hits this point, carbon and oxygen can fuse into progressively heavier elements. In fact, they can fuse all the way up to the 26th element on the periodic table, which is iron. And then at that point, you've reached the peak of the binding energy per nucleon curve, and you only get energy out of fusion when you're on the rising part of that peak. And so once iron has developed in the core of such a star, and you can see it's surrounded by shells of progressively lighter elements, the results of previous rounds of fusion. Once iron is built up, you're done as a star. And really, within a day or so of developing this iron core, your fate is sealed, okay, at this point. It's a horrendous situation for a star to be in because there's no new fuel source in the core, and these other layers of fusion here are just dumping more mass onto the core. And once it hits probably about 1.5 times the mass of the sun in the core, the whole thing just implodes. In less than a second, the core goes from something the size of maybe the Earth down to something the size of a small city. And in that collapse, protons and electrons essentially get squeezed together to form neutrons. And when this ball of collapsing neutrons reaches, maybe it's about 10 kilometers across or so, It halts when neutron degeneracy pressure exerts its force, and you have the birth of a neutron star in the core of this imploding massive star. The rest of the star keeps falling in, though, and smashes into this newly formed neutron star. And in the conventional theory, a spherical shock wave develops, pummels its way out through the envelope, and ejects it out into interstellar space. And it announces itself with a brilliance that for a time is over 1 billion times the luminosity of the sun. This is the origin of a core collapse supernova, and this is the exact fate that we think awaits Betelgeuse. The problem is we don't know what's going on in the core of Betelgeuse. If it's just started to fuse helium into carbon and oxygen, it could have up to 1 million years left in its life. On the other hand, if it's developing that iron core right now, it's going to explode tomorrow. And so we're a bit uncertain about exactly when it's going to explode, and we can't really tell by looking at its surface, even if it's doing some strange things on the surface. But this is what happened for supernova 2008 BK. I want to note supernovae do arise from other types of stars, but we can always tell the most common type of explosion when a red supergiant explodes. We can always tell, even without previous pictures, because when a red supergiant explodes, the light curve, the plot of its brightness as a function of time, has a very characteristic shape to it. When the star explodes, this is the light curve of the supernova 2008 BK I've been showing you. When the star explodes, it stays at about the same optical brightness for over 100 days, and then it plummets. And this part of the light curve is called a plateau. It's the only kind of supernova that has this light curve. And when you see this, it's always a red supergiant exploding. And the reason is that this core that's imploding is imploding inside a very thick, massive, intact hydrogen envelope. And when it explodes, it inserts all of the explosion energy, the shock deposited and radioactive decay energy that's released in the explosion. It inserts that into this expanding remnant of a hydrogen envelope that starts out completely opaque and then recombines as the hydrogen atoms recombine over time. But think of the envelope as like a blanket that holds up the light curve. It doesn't let it all come out at once. So it comes out slowly over a period of several months, and it keeps it at about the same brightness in our sky for about 100 days. So this kind of supernova is known as a type 2 plateau supernova, type 2P. And it's actually the most common kind of core collapse supernova. It's a great story, actually, when you're looking at a type 2P supernova, because the longer you look at it, the deeper into the heart of the explosion you see. In the beginning, you're seeing just the outer layers, and by the time it plummets off of the plateau, you're seeing right into the core, into the guts of the explosion itself. So it's a story that reveals itself over time, and it rewards patience as well. So that's the kind of generic story for how a core collapse supernova is born. I say generic because I have to let you in on a secret here. And that is that exact scenario I just presented to you, it doesn't work. It was first proposed over 60 years ago. You can see here in the original paper by Sterling Colgate. The spherical shock model, unfortunately, when we try to simulate this using a computer to generate the explosion, the shock always stalls as it's trying to get out of the outer core and eventually just gets sapped of its energy and kind of gives up and just implodes, and you just get a whole imploding star with no fireworks, no supernova. Nature knows how to explode these stars because about once per second in the universe, one of these stars is exploding. And so it was pretty quickly recognized that the conventional model didn't work. And so over the last 60 years, we've come up with some ingenious ways to try to get the thing to explode. One of the first ideas was to try to tap into a little bit of the energy that's being released in a supernova in neutrinos. The vast majority of the supernova energy just disappears in neutrinos, and there's the idea that if you could trap some of that energy and get it to help reinvigorate the shock, you could get the thing to explode. However, various modelers can't get this mechanism to work either. It's led us to question whether we're just missing something very fundamental about the explosion. And there's no shortage of ideas out there. Many of them are very creative. Some of them are pretty exotic. And they're all pretty powerful. Here, calling for a magnetohydrodynamic jet to aid with the explosion. But at the end of the day, when you sit down and read any honest modern review of our understanding of core collapse supernova theory, it usually contains a sentence, just like Adam Burrows put in here. But what is this process by which a star's multi-million-year life is terminated abruptly and violently within seconds, then announced over months via the brilliant optical display that is a supernova explosion? 50 years of theory, calculation, and observation have not definitively answered this question. It's this final point that I'm going to focus on today: observation. Okay, what do observations tell us about the nature of the explosion? And in a very particular type of observation I'm going to focus on today, before returning at the end of the talk to a little bit of theory. A key aspect of getting a clue to the explosion mechanism is its geometry. Conventional model predicts a spherical explosion. Most of the more exotic ideas for what's triggering the explosion do not. They are generally highly asymmetric. And therefore, a bottom line fundamental observational question is just to ask whether the most common type of stellar explosion, the type 2p supernova, is in fact round. And that is why I'm so interested in the explosion geometry of red supergiant stars. If betelgeuse would just go ahead and explode already, we could probably answer this question much more easily, because we could resolve the actual explosion. But until we get one that's that close, we're limited to extragalactic supernovae, which always remain unresolved, just a point, even with our best telescopes. So how can you determine the geometry of the explosion from looking at a point source? The good news is nature has encoded information about the geometry of the explosion in the polarization property of light. By studying the polarization of supernova light, we can get a handle on whether these things are spherical or not. And here's how it works. All young supernova atmospheres are dominated by electron scattering. Photons are produced interior to a region of electrons that scatter the photons, and electron scattering is a highly polarizing process. Indeed, if we were so lucky as to be able to resolve a young supernova atmosphere, we would expect to measure changes in the polarization degree and direction as a function of location in that atmosphere. A photon that gets forward scattered to you has zero polarization. Photons that get scattered at right angles, okay, have 100% polarization, okay, and all the values in between. For a point source, all you can measure is the net polarization, the total polarization. And the idea is, if the thing is spherical, or at least presents circular symmetry in the plane of the sky, you measure the number 0. The polarization is 0. If something breaks the symmetry, then you get a net polarization. You don't get complete cancellation. So for these unresolved supernovae in external galaxies, all we can really measure is the net polarization. So let me tell you the story about what has been discovered about type 2p supernovae. And it's a story that's going to have 3 time points in history The first one's going to be about 20 years ago. Second one's about 14 years ago. And then the last one is 5 days ago. So this is a pretty current talk that I'm giving you here. So first, 20 years ago, as part of my PhD thesis on the geometry of supernova explosions, I measured the polarization for a number of type 2p supernovae. I have to point out it wasn't the most exciting thesis because I became expert at measuring the number 0 to various degrees of certainty. But let me tell you, it's really hard to measure the number 0. So here's the polarization, the net polarization we measured for a bunch of supernovas with error bars as a function of time, as a function of day since explosion. And these are all for type 2p supernovae. So there's one, so measuring 0 kind of tells you the thing seems spherical or round in the plane of the sky. But there was always one huge caveat to these studies. All of our data, as well as data taken by other people, had been taken during the plateau phase of the supernova's development. But let's revisit what's happening during that time. At the beginning of the plateau, the entire hydrogen envelope is ionized. It's an expanding, opaque fireball. The photosphere is way out in the outskirts of the envelope. Red supergiants exploding, though, reward patience because as time goes on, the envelope cools from the outside in, and those electrons begin recombining onto the hydrogen nuclei, protons, and they go from an opaque to a transparency. And that recombination front just recedes back through the envelope with time until reaching the core here where it falls off. And so the fact we were measuring 0 out here on the plateau might have just been telling us about the outer parts of the geometry. What about the inner parts? Well, this is a fleeting phase here, and you need electrons still around to scatter and tell you the geometry. But kind of the holy grail was always to try to catch one of these objects as it was falling off of the plateau. And fortunately, we got a chance to do that in 2004. So this is the second time point. With supernova 2004 DJ here in NGC 2403. And let me show you what we saw. First of all, this type 2 plateau supernova was only discovered as it came out from behind the sun in the sky. So we only caught the last part of its plateau. We don't have the first part of the plateau in the light curve or any data points. But we started getting data on it right here at the end of the plateau. And I'm going to kind of walk you through this. Our first data point came here towards the end of the plateau of this supernova. And I again measured the number 0 for the polarization. The next point here, still 0. The next point here, still 0. But then we finally got this point, kind of the point I always wanted to get on one of these supernovae. And at that point, the polarization shot up. And when I say shot up, I still point out it was only 0.5% polarized, but that's a lot in supernova polarization. And we, of course, continued to follow the development of this object and watched the polarization drop, okay, as the optical depth to electron scattering became smaller and smaller, and spectropolarimetry lost its probe of geometry as time went on. But the idea was here we'd caught for the first time in a normal core collapse supernova, the asymmetric core revealing itself. And the idea was even a highly asymmetric explosion could spherize as the shock propagates through the outer layers. So the big question was whether this supernova was somehow unusual or whether this would be a common occurrence. So a group was formed specifically to investigate asphericities in supernovae of all types, including the type 2Ps. It's called the Supernova Spectropolarimetry Project, SNSPOL, and it continues on to this day. And other groups as well have continued to gather spectropolarimetry polarimetry of collapsed supernovae. And many type 2p supernovae showed the same characteristics that O4DJ did, spikes right at the end of the plateau. But there have also been some curious ones that show different behavior. And I'm going to start building up the data set here by putting everything on a single plot. I've started here with the supernova I've already introduced you to, supernova 2004 DJ. Here's the end of the plateau, and here are the polarization points with squares. This is the light curve. These are the polarization measurements over here. The next supernova that I'm going to show you the data for is actually the one I've been talking about before, supernova 2008 BK itself, a classic type 2 plateau supernova. And its polarization characteristics were a bit different than supernova 2004 DJ. It started rising in polarization well before the end of the plateau and achieving about the same overall degree of polarization, but much earlier. And so the idea here might be that the asymmetry penetrated further out into the envelope for this supernova than it had for supernova 2004 DJ. At this point, I want to actually dig in a bit and show you the actual data that we get on these objects. I've kind of been shielding you from the goriness of what is really spectropolarimetry. What I'm showing you in these plots is an average over a wide wavelength band. But we actually have much more detail about the nature of the asymmetry by looking at the polarization as a function of wavelength. No, this is what's known as spectropolarimetry. So I'm going to show you the actual spectropolarimetry for supernova 2004 DJ at its point of maximum polarization and supernova 2008 BK at its maximum. First, this is what supernova 2004 DJ looks like. So on the x-axis here, this is rest wavelength in angstroms. This is what astronomers use. This is the visual part of the electromagnetic spectrum. And this curve up here is just what's called the flux spectrum. This is the normal spectrum of a supernova, showing features due to hydrogen, calcium, and so forth. This is the polarization as a function of wavelength. And you can see it's a very complicated signature that we see for supernova 2004 DJ. But what was very curious was that in other events, event after event after event, if we plotted the spectropolarimetry when it achieved near its maximum, it looked very similar to this. Let me show you the spectropolarimetry of 2008 BK. It's a virtual carbon copy. Whatever is producing the asymmetry is doing it with the same signatures. And so it seems like something very common is at work in the explosions of these red supergiants. So let me continue the story. The next object I want to show you is a supernova from 2012. It's known as supernova 2012 AW. And it kind of has the opposite problem to supernova 2004 DJ. This is the photometric light curve of supernova 2012 AW. We get the whole plateau, and then it starts dropping off, and guess what? It went behind the sun. We still can't observe these things when the sun gets in the way. So we missed the rest of the drop off the plateau. But what it showed us before it dropped off was really extraordinary. Here's the polarization at several epochs for supernova 2012 AW. It was just a monster. It was just ramping way up, okay, 3 times the degree of polarization. And it started very early on and just rose to an incredible amount of polarization. Curiously, when we look again at the spectropolarimetry and we compare the actual data of 2012 AW with the other two, we find that although the degree of polarization is certainly much higher here, the specific features feature for feature, are eerily similar to what we've seen before. So more polarization, higher degree of asymmetry, perhaps penetrating further out into the envelope here than before, but the same basic signatures. All right, this brings me to the third and final time point in this study, which is literally 5 days ago, when my colleague Luc Desart and along with John Hillier and Juliana Pinata submitted a paper just 5 days ago, which was really the culminating work of everything that Luc Desart has done for the last 8 years. He's basically spent that time trying to construct a theoretical model that will fit the observations that we see to supernova 2012 AW. And I'll spare you all the details of the computer modeling that he did, but he essentially built a 2D radiative transfer code that models the wavelength and time-dependent polarization of type 2 plateau supernovae with various asymmetries imparted to them. Remember, a spherical electron scattering environment gives you zero polarization, so you have to break the asymmetry. And what we did was assume that as part of the explosion, there was a clump of enhanced ionization out in the outer ejecta of the expanding supernova, which yielded enhanced free electron density out there, breaking the symmetry of the electron scattering atmosphere. And I'm going to show you the results of one of the simulations that we ran that had a cone of enhanced electron density about 50 degrees wide, situated far out in the ejecta. First thing I'm going to show you is the result of the spectropolarimetric modeling, and it's comparing it with what was seen for supernova 2012 AW. So the model here in red and the actual data, this is the point right near the end of the plateau. And as you see, we get the model really close to what the data actually show us, indicating there is a severe asymmetry in the ionization in the outer, that's kind of the surprising part, the outer ejecta of supernova 2012 AW. We know it's out in the outer parts because we actually took this asymmetry and modeled it through the first 120 days of the supernova's development and charted its course, and we're able to replicate the polarization seen in 2012 AW with the models. So this is a plot. These are the black circles here are the light curve of the supernova. The diamonds are actually our prediction for what the light curve should look like. Polarization is down here. This is the black circles are the continuum polarization measured for the supernova, and the diamonds were what the models predicted. And this is for a constant source of ionization. So we didn't tweak it for each epoch. So it was consistent through the whole thing. This shows the model's prediction for what we would have seen at 160 days, but we don't have data there. So we don't actually know if the model could fit all the way out there. So the jury seems to be in that there is a fundamental asymmetry in the explosions of type 2p supernovae. What's producing these asymmetries that we see? We have this observational clue. The theory needs to catch up. The clues appear overwhelming, that there's something non-spherical that must be driving most, if not all, stellar explosions. Are the explosions driven by magnetohydrodynamical jets? Are they perhaps being formed through a delayed neutrino channel, asphericities produced by turbulence or shock instabilities? Much more work needs to be done on the theoretical mechanism. There's still no consensus, but the observational fact at this point is that whatever is producing the explosions of nature's most massive stars is doing so in a highly asymmetric manner. Bottom line, when Betelgeuse explodes, and I do hope it's tomorrow, we'll get quite a show. and we'll probably learn a lot about the explosion geometry, a lot more about the explosion geometry of red supergiant stars. So I'll end there and take any questions that you may have.
Thank you, sir, for your wonderful presentation, sir. I think students have learned a lot of things about the supergiant star. So I have got one question. So how do supernova show us that the universe expansion is accelerating? Is there any relation?
Yeah, absolutely. Let me just get back here so I can see you. So the accelerating universe discovery back in the late 1990s came from observing not this kind of supernova, which is a type 2p supernova, but rather a type 1a supernova. In the talk, I mentioned that most stars end up as white dwarfs, and I may have led you to believe that the white dwarf just will sit quiescently forever and ever and ever and do nothing else. But in fact, if there's a companion star next to the white dwarf or something feeding it, you can actually trigger the white dwarf to explode as what's called a thermonuclear supernova. And this is called a type 1a supernova, and they're extremely luminous, and they are extraordinarily good standard candles. When they blow up, we can tell what their luminosity is intrinsically, and by measuring how apparently bright they appear in the sky, we can get very accurate distances to type 1a supernovas. And it was in the 1990s, and it was actually one of the groups was part of the group I was with at UC Berkeley, that we first started measuring distances to type 1a supernovae, not just nearby, but billions of light years away. And by so doing, by plotting the distance and redshifts of these type 1a supernova, led to the, at the time, very surprising result that the expansion rate of our universe, instead of slowing down, which is what we thought we all did, was actually speeding up or accelerating in its expansion. So different type of supernova and a different use, using them as distance indicators rather than trying to figure out the physics of the explosion.
Thanks, sir. We have got another question in the inbox. So, which type of supernova was responsible for forming planet or Earth, our Earth?
I'm sorry.
So, which type of supernova was responsible for forming planet?
For forming a planet?
Planet, yeah.
So, okay, I'm going to take this question very broadly, and that is, our universe in its earliest days had only hydrogen and helium. Planets are made out of much heavier stuff. Like our planet, the Earth, is made out of predominantly iron and very heavy elements. And the only way really we know of for such things to get, for such heavy elements to get produced, are in the cores of stars during their lives. And the best way to spread that material out into space is through a supernova explosion. And all the stuff, literally, that our planet's made out of, the heavy stuff, is probably the debris of past generations of exploded stars. So that's really what we're made out of. I'm not sure if I'm answering the question the questioner asked, but that's how I'm taking it.
Thank you, sir. There will be another question. This may be the last. What will happen with our sun at the end?
Yeah. So our sun is going to go through a much less dramatic ending to its life. Like the high mass stars, our sun is going to blow up and become a giant star. It's just not going to be a supergiant. Astronomers run out of adjectives. But stars like our sun will puff up, and current calculations suggest that our sun will actually puff up to almost the orbit of the Earth. So we may escape actually being inside the sun during its red giant phase, but our sky will be completely just a huge red giant atmosphere in our sky, and it will have swallowed up Mercury and Venus, and at that point it will have evaporated our atmosphere, and our planet will be a really crummy place for us to be living. So fortunately, this is about 4 or 5 billion years away. But if we're still around at that point, I hope we've colonized another planet around another star and can just look back at the sun and see a beautiful planetary nebula in the sky as it dies. So the fate of our sun is to then become a white dwarf. And since it's alone, there's no other star nearby, we think it's just going to cool off for the rest of time as a cold white dwarf. So much less dramatic than the explosions of these high mass stars.
So thank you, sir, for your wonderful presentation and discussion session, sir. I think students have learned a lot of things. So about red supergiant stars. So we have started this program actually to encourage and our student and motivate our student in this corona pandemic situation. So I think we have actually a little bit successful in doing this, because we have completely successfully completed our 114th, and today it's 115. So we're trying to do that things. So thanks again, sir, for accepting our invitation and giving me chance to arrange an wonderful webinar with you, sir. And hopefully in near future we will arrange another webinar with you, sir, for our student. So thanks again, sir.
Thank you
Bye
very
for
much.
today.
It was fun.
Good night to your part, sir.
Good night.
Yeah, bye.